Alright, so in this video, we are going to talk about work and possibly kinetic energy. It would help if you keep the chapter 6 and 7 PowerPoint open in front of you. This lecture is going to follow the PowerPoint pretty closely. Okay, so the first concept that we are going to discuss is the concept of work. So what is work? Suppose, and we are going to talk about the work done by a constant force. So that's the first thing that we're going to discuss. And the definition of work done by a constant force is given on slide 3, which is where I am. Okay, so here's the definition of the work done. Suppose you have an object which is sitting on the ground like this, and you exert a force F on the object, and that force moves the object from here to here. So the object was over here, it moved over here. Let's say that the displacement vector of the object is the vector d, and the object moved in a straight line. So in that case, the work done by this force is defined as F dot d, the dot product of the force and the displacement, which can also be written, as you remember from chapter 1, magnitude of the force multiplied by the magnitude of the displacement multiplied by cosine of the angle between the force and the displacement. So this angle here, theta. Notice that if you put the arrow on top of a vector, like I have the arrow over the F, it means the vector F. But if you write F without an arrow, that just means the magnitude of that vector. Okay. So this is the definition of work, and it's very important to remember that this definition only applies when two conditions hold. Number one, when the force is constant, and number two, when the object moves in a straight line. So if neither of these conditions, if these conditions don't hold, or even one of these conditions doesn't hold, then you cannot use this simple definition, right? So this definition only applies when both of these conditions hold. All right. The unit of work is a joule in the SI system. And what is a joule? Work is force multiplied by distance. So force is in newtons, distance is in meters. So Newton times meter is defined as a joule. All right. You'll see later on that joule is also the unit of energy. There's a little bit of terminology involved here. So if the force and the displacement make a acute angle, so suppose the force is like this, and as a result of this force, the object moves from here to here, let's say. So this is the displacement vector. So as you can see, F and D make an angle which is acute or less than 90 degrees. Then clearly the work done will be positive. So the formula for work is FD cosine theta. If theta is less than 90 degrees, then it's a positive number. F and D are magnitudes of vectors, so they're always positive. So that means the work will be positive then when work done is positive, we say that the work is done by the force. Okay, now suppose the force and the displacement make an obtuse angle. So force is in this direction, displacement is in this direction, and the angle between them is greater than 90 degrees. So in that case, work is going to be negative. So in that case, we say that the work is done against the force. Now, you might be wondering, if the force is acting in that direction, to the up and to the left, how can the object possibly move to the right? If you think about it, there's many ways in which that might happen. the object might already be moving to the right very fast when you started applying the force. So it keeps moving to the right for a while. That's one possibility. Another possibility is that there might be more than one force. So there might be other forces which are pushing the object to the right. So in any case, if the force and the displacement make obtuse angle, then the work done is said to be negative, and negative work is referred to as work done against the force. Okay, there's one more case. What happens if the force is in this direction and it's at right angles to the displacement? So in that case, the work done is 0. Work is f d cosine theta. In this case, it's going to be f d cosine 90 degrees, which is 0, as you know. So in that case, no work is done. So if the force and the displacement are at right angles, then the work done is 0, right? So colloquially, you can see that work is done by a force, or in other words, positive work is done when the force kind of gets its way, right? As you can see happening in situation 1. If the force is not getting its way, which is what's happening in situation 2, then we say that work is done against the force. And whichever force was pushing to the right clearly did positive work, and so that force got its way. But the force F in situation 2 did not get its way, right? All right, okay. Now, there's another important concept here, which is the concept of net work. Suppose you have multiple forces acting on an object. So let's say that you've got one force acting in this direction and another force acting in that direction. And the object moves maybe from here to here. So in that case, you can calculate a net work done. So you can calculate the work done by the force F1. You can calculate the work done by the force F2, and you can add them up, and that will be the net work, right? So let's just look at an example. Suppose this angle is I don't know, 135 degrees maybe, and this displacement is 1 meter, and let's say F1 is 1 Newton, F2 is 2 newtons. Okay. All right. So what is the net work? So let's calculate the work done by F1. So it would be force multiplied by, so the formula for work, as you know, is F d cosine theta, right? So the force is 1 Newton multiplied by 1 meter multiplied by cosine of 0, which is 1, right? So that's going to be 1 joule. So F1 is doing 1 joule. You can see that it's coming out to be positive. That's obvious because F1 is getting its way, right? What about F2? So the work done by F2 would be 2 newtons multiplied by 1 meter multiplied by cosine of 135 degrees, because that's the angle between the force and the displacement, right? So what is that? Let me just calculate that. So that's minus root 2 minus 1.41 joules. So what is the net force done on the object? What is the net work done on the object? So the net work, if these are the only two forces acting on the object, the net work would just be minus 0.41 joules. So this is the net work done by F1 and F2. In reality, if the object is really moving in a straight line like this, there has to be some other force acting on it as well, but that would be more forces, so more work for us to calculate. So I'm just showing you an example of how you add up work. Notice that work is a scalar, so you don't you just add or subtract the amount of work. So it will be a positive or a negative number, and when you combine different amounts of work, you just add them up like we did over here. All right, so the net work is simply the work done by all the forces acting on the object, right? The total amount of work done by all the forces acting on the object. Okay, so let's look at a few examples, a few more examples. So in my PowerPoint, you'll find that certain problems are fully worked out on the slide. So for example, this problem, if you go to the presentation mode and then you just click through it, you should see the solution show up step by step. That is not the case for all the slides, but some of them do have a solution on them. So always, so for any problem, just check whether the solution is already on the slide by going into the presentation mode. Okay, so I'm going to skip this problem because it's already worked out on the slide. Let's take a look at take a look at this problem. Okay. So I'll let you read this problem yourself and see if you can set it up. And you should always, whenever you're watching these videos, you should always pause a video when I show you the problem, and see if you can set it up yourself, and only then move on to seeing how I work it out. Okay, so let's give this problem a try. So we are working on the problem on slide 8. A person of mass 60 kgs is doing chin-ups. During the ascending phase, her body rises by a distance of 0.7 meters starting from rest, and her velocity at the top position is 1.5 meters per second. Okay, so we're just going to draw the person as a point mass, right? And this person is exerting, the hands or the arms of this person are exerting an upward force on her. And as a result of that upward force, and we're just going to assume that that force is it's a constant force. So the result of that force is that she moves from her starting position to the top position up here. And when she gets up there, she has a velocity of 1.5 meters per second. So she's starting with a velocity of 0. And over here, she has a velocity of 1.5 meters per second. Okay. And this distance is given. This distance is 0.7 meters, right? Okay, mass of the person is also given. So the first question is, what is the force that she must exert with her arms? So you have to calculate the force F. Now, this question has nothing to do with this chapter. This question is an application of the material that's covered in chapters 4 and 5, Newton's laws, in particular Newton's second law. So to calculate the force F, what we need to do is we need to draw a force diagram on this person, and then just apply Newton's second law. So standard procedure. What are all the other forces acting on this person? So one force is the force of gravity, mg. And that's pretty much all the forces acting on the person. So there is the external force, I mean the force exerted by the arms, and the force of gravity, right? So let's apply Newton's second law in the vertical direction. So what is Newton's second law? Newton's second law is F net, the net force, equals mass times the acceleration, right? So the net force in this case is, for that you just add up the vector force arrows. So I see one arrow pointing upwards, another arrow pointing downwards. We can choose the sign convention that upward is positive. So our sign convention is upward is positive. The plus VE just means positive. So I'm going to give the F a positive sign, mg a negative sign. So on the left side I have F minus mg, and on the right side I have mass times acceleration. So now I just need to know what the acceleration is, and then I can solve for F. So how do I find the acceleration? That is a chapter 2 problem. You are given a distance, you have the initial velocity, you have the final velocity, and you have to find the acceleration. So when the acceleration is constant, or when all the forces are constant, you can use kinematics. So you use the kinematic equations to find the acceleration, right? How would you do that? You would, okay, what are the kinematic equations? So one of them is V final square is equal to V initial square plus 2, okay, I'll just not start with this one. Let's just write down the other ones. So the first kinematic equation is V final is equal to V initial plus acceleration multiplied by time. The second kinematic equation is x or y final is equal to x initial. It's probably just better to use y rather than x. So y final equals y initial plus v initial times t plus half a t square. And the third kinematic equation is v final square equals v initial square plus 2a y final minus y initial. Okay, so I just arbitrarily call this one the first kinematic equation, this one the second kinematic equation, and this one the third kinematic equation. Okay, so let's see which of these we can use to find the A, right? So you can choose y initial to be 0 over here. And in that case, y final over here is 0.7 meters. All right. So see if you can figure out which equation we would want to use. It looks like the third kinematic equation is our best bet in solving for A, right? So let's plug everything into this third kinematic equation. Our V final is given 1.5. So 1.5 square. V initial, so she's starting at rest, so V initial is 0. 2 times A times y final minus y initial. That's basically just the distance that she covered. So that's going to be 0.7 meters. So from here we can solve for A. So A would be 1.5 square divided by 2 times 0.7. So you can just calculate that. Let me calculate that. So it's 1.5 square divided by 2 times 0.7. So that's 1.6. 1.6 meters per second square. That's our acceleration. Now we can go back to Newton's second law and write that and plug that in. So we had F minus mg is equal to ma, right? We know the A now. So F is equal to mg plus A. All right, so we know the mass of the person, it's 60 kgs. What should I plug in for g? A very common misconception is that I need to plug in negative 9.8 for g, but that's not what you need to plug in. You should plug in positive 9.8 for g, and A we already found was 1.6, right? So what does that come to? 60 times 9.8 plus 1.6 gives 684. So approximately 684 newtons. And that is the force that she needs to exert. Now, why did I plug in positive 9.8 for G? The reason is that when you say G is negative 9.8, the negative simply represents the direction of the acceleration due to gravity, assuming that your sign convention is upward, is anything pointing upward is positive, anything pointing downward is negative. So you have already taken the sign of G, the direction of G, into account when you wrote down Newton's second law. So we have, that's the reason we have F minus mg, right? So we've already taken the negative into account. The negative is just the direction. So we've already taken the direction into account over here. There is no need to plug in, use negative anymore after that. So that is why you need to plug in positive 9.8. So you can see that the force is 684 newtons. That's the force that she needs to exert with her hands. There's an interesting thing here. The weight of the person is just mg, right? So what is the weight of the person in newtons? The person is 60 kgs mass. G is approximately 10. So approximately the weight of the person is 600 newtons. So you can see that she has to exert a force of 684 newtons, which is a lot greater than her weight, her own weight, in order to lift herself up, right? That is the reason a pull-up or a chin-up is a very difficult exercise, because you have to exert a force greater than your body weight in order to lift yourself up. And so unless your arms are pretty strong, you're not going to be able to do it. That's why most people have difficulty doing push-ups, doing pull-ups or chin-ups. Okay, so that's the first part of this question. The second part is asking, what is the work done by her during the ascent? So what work is she doing? What work is this force F doing in lifting herself up, right? So for part 2, to calculate the work done, since the force is constant, you can use the simple formula for work. Work is force multiplied by distance multiplied by cosine of the angle between the force and the distance, right? Displacement. So the force is 684 newtons. The displacement is 0.7 meters. And what is the angle between the force and the displacement? So the force acting on her is upwards. She is moving upwards. So the force and the displacement make an angle of 0 degrees. So it's cosine of 0, which is 1. So if you do 684 times 0.7, you're going to get something like 479 joules. Okay. So that is the work done by her during the ascent. We might as well calculate one other thing, which is not asked for on the slide. What is the work done by gravity? So I'll call that Wg. So the force of gravity is going to be mg. So again, we are using the same formula, Ft cosine theta. The force of gravity is mg, right? So it's going to be 60 multiplied by 9.8. That's the F. The displacement is the same. It's 0.7. And what is the angle between the force of gravity and, I should just call this Fg to be clear. What is the angle between the force of gravity and the displacement? Now, the force of gravity is acting downwards and the displacement is upwards, right? So, the angle between them is clearly 180 degrees, right? Cosine of 180 is -1. So the work done by gravity is going to be, might as well calculate this. (60 times 9.8 times 0.7, which is 411, negative 411, about 412, negative 412 joules. Right? Okay, so that is the work done by gravity. We might as well calculate one more thing. It's also not asked in the slide. What is the net work? The net work is going to be the work done by the person plus the work done by gravity. You have to take the signs of the different amounts of work into account. So the work, and that's all. That's the work done by all forces on her. Those are the only two forces on her. So the net work would just be 479 joules minus 412 joules. So that's going to be 479 minus 412. So that's going to be 67 joules. So the net work is 67 joules, right? Okay. So the work done by gravity and the net work were not asked for on the slide. We just went ahead and calculated them. The last question on the slide is, what is the physical significance of this work that she did? So 479 joules, what is the physical significance of this? So this is something that will become more and more apparent as we move on in the chapter. But the physical significance of work is that it's a transfer of energy, right? So she is, so this 479 joules of work is basically energy that she's taking from chemical form stored in her body and converting that into potential and kinetic energy, right? So it's this transfer of energy, this accounting for energy is what work is. Work always accounts for how much energy is transferred to a system by a force. And this will become clearer as we move along. All right. I have a very similar example on the next slide, which is slide number 9. So please try the problems on slide number 7 and slide number 9. Slide number 9 is very similar to this problem. Okay. All right. So these are all examples of work done by a constant force, and when an object is moving in a straight line. So remember, there were two conditions for work. Oh, I don't have that. So there are two conditions for applying the simple formula for work, which was W equals F d cosine theta. So this applies when the force is constant and the object is moving in a straight line. What happens if these conditions don't hold? How do you calculate the work done? So if the force is not constant and the object is also not moving in a straight line, then the work has to be calculated by something called a line integral. Since we are a bit short on time, I'm not going to cover line integrals for now. So we will just see what happens if the force is variable, but the object is still moving in a straight line. So that is not too difficult to figure out. So suppose the force is variable and the object is still moving in a straight line. So how do you calculate the work done by the force in that case? So we have an object that's, let's say it's moving from here to here, and it's not feeling the same force. So maybe the force was represented by this vector over here, but by the time it's gotten to this point, the force is completely different. The force might be in the opposite direction. And then when it's over here, the force might be again in this direction, but very strong. So the force is in the same straight line, and the object is also moving in a straight line. So the force is not constant. So how do you get the work in that case? The idea is very simple. You break up the path that the particle is following. Let's say the particle moved from here to here. You break up this path into very, very tiny segments, right? Call each tiny segment as dx, right? And this segment dx is so incredibly small that you can ignore the fact that the force is changing at every point. You can assume that the force is approximately constant over the distance dx. So if the force is constant over the distance dx, then we are allowed to use the simple formula for work. So let's call the tiny amount of work done as the object moves from, let's say that this is x, this distance is x, and this distance is x plus dx. So the tiny amount of work done as the object moves from x to x plus dx is going to be f, whatever the value of f is at x, times the distance dx, times cosine of the angle between f and dx, which is 0. So we're just going to allow for f to be positive or negative. And so the angle between f and dx is just 0, because they're both in the x direction. So the work done, this tiny amount of work we are calling dw, is going to be f dx, f of x dx. Cosine 0 is just 1. So dw is f of x dx. And so the work done, the total amount of work done as the particle goes from point A to point B, so from x equals A to x equals B, would just be the integral a to b f of x dx. And that is how you find the work done by a variable force in one dimension. In principle, you can also have a situation where the object moves in 2 or 3 dimensions. So suppose the object starts from point A over here and goes to point B over here, and the path is this weird path, not a straight line at all. And also the force is completely different at each point. So over here the force might be in this direction with this magnitude. Over here the force might have a completely different magnitude and direction. Over here again the force might have a completely different magnitude and direction. How do you find the work done in a situation like this if the object is moving in 2 or 3 dimensions? The answer is you use something called a line integral, as I just mentioned. And it's written like this for those of you that are familiar with line integrals. It's f dot dr. So it looks similar to what we just did. But as I said, we are not going to get into the details of how to calculate line integrals. It's not going to be that important in this course. Okay. So this is called a line integral. And we are not covering it. Okay, so that is how you calculate the work done by a variable force when the object is not moving in a straight line. Okay. All right, so let's look at an application of the formula that we just derived. So that this is slide 12. This is the problem on slide 12. So a particle is subjected to a force given by f of x equals 2 plus 3x newtons. How much work is done by the force in moving the particle from x equals 0 to x equals 2. So the particle is moving on the x-axis from 0 to 2. And the force has a different value. It points along the x-axis, but it has a different value at each point on the x-axis, right? So it's a variable force. It's not a constant force at all. So if it's a variable force, then you have to do work is integral f of x dx from the starting point to the ending point, which is 0 to 2. And I'm sure you can just do this on your own. 0 to 2, 2 plus 3x dx. If you are rusty on calculus, then now would be a very good time to brush up on your calculus. And if I've done the math correctly, then the answer on the slide would be what you get, 10 joules. All right. Now, the next thing that we're going to talk about, it's a very, very important concept. It's conservative and non-conservative forces. Okay, so what are conservative forces? Now, suppose you have a situation where the force can be different at each point in space. It's just what we were discussing. So suppose if the particle is over here, the force on it is like this. When the particle is over here, the force on it might be like that. When it's over here, it feels another force in this direction. So the force is position dependent, and at each point in space, the force has a different magnitude and direction. So this kind of force is called a vector field, right? So this kind of force is called a vector field. Which basically means that different magnitude or the magnitude and direction of the force, I'll just write that as F, depends on position. So suppose you have a force like this, then if a particle moves from one point to another along some path, the work done, so let's say the particle moved from here to here, right? And so it encountered a different force at each point on its journey, right? Okay, now suppose the particle follows a different path to go from the same starting point to the same ending point. So I'm just going to draw the different path with a different color. Let's say the particle followed this path. So this was path number 1, and this was path number 2. Do you think the work done would be the same along both the paths? Along the second path, the particle encountered completely different forces, let's say. So the forces were all completely different on the second path, right? So there's really no reason to expect that the work done along path 1 would be the same as the work done along path 2. And if you consider yet another path, again, the forces would be completely different along path 3. So the work done would be completely different. So you would expect different amounts of work for each path, right? And that's naturally what you would expect. However, there's a remarkable category of forces which are called conservative forces, for which the work done does not depend on the path. The work done does not depend on the path. That is the definition of a conservative force. The work done by the force is not dependent on the path. You might think that how can that be possible if the force is different at different points? So each path the particle encounters completely different set of forces. Well, conservative forces are magical like that. So no matter which path you follow, the work done is going to be the same. That's what a conservative force is. There's an alternative way of defining a conservative force, which is that if you go in a closed path, so you start from A, go to B, and then come back to A. So if you do a closed loop, the total amount of work is 0. So total work done by the force over a closed loop is 0. That is the definition of a conservative force. That's an alternative definition of the conservative force. You can prove that both of these definitions are identical. We are not going to get into the proof. So that is a conservative force. What's an example of a conservative force in real life? There are 2 conservative forces that you'll see in this chapter. One of them is gravity, and the second one is called the spring force, which we are going to learn about in just a little bit. Okay, so these are the only two conservative forces that you're going to see in physics 1. In physics 2, you're going to see one more conservative force, and that's called the electrostatic force. Okay, so now that I've told you what a conservative force is, you can easily, you can almost guess what is a non-conservative force. A non-conservative force is one in which the work done does depend on the path taken, right? So you get, if you follow this path, or if you follow this path, you'll get different amounts of work. So work done along path 1 is not the same as the work done along path 2, and so on. So that's a non-conservative force. What's an and also for a non-conservative force, if you start at a certain point and then you do a closed loop, come back to that point, the total amount of work done is not going to be equal to 0, right? So just the opposite of the definition of a conservative force. So what's an example of a non-conservative force? Friction, air resistance, these are all non-conservative forces. They're also called dissipative forces. So friction is the most important non-conservative force that you're going to see in this course. Okay. All right. The next thing that we're going to talk about is the spring force. So what is the spring force? Suppose you have a spring, and this is on slide 15. Suppose you have a spring. All of you know what a spring is. It's just a coil, a coiled wire. Suppose you've got a spring, and you leave the spring to itself. Like you've attached one end to a wall, and maybe it's sitting on a frictionless surface. I'm not drawing the surface underneath it. So you leave the spring to itself. You don't mess with it. So then the spring has a certain natural length, and that's the length that it likes to be at when you're not messing with it. So let's say that the way I've drawn the spring here, the right end of the spring is at its natural length, right? Now what would happen if you stretch the spring? So let's say that I take the same spring and I stretch it out. So the end of the spring is over here, right? So at this point, the spring will not be happy to be stretched out. So there will be a force acting on your hand trying to pull the end of the spring back. So let's represent that force by this arrow. And let's call this force F, right? Okay, so that is the force with which the spring is pulling back because it wants to get back to its natural length, right? Let's say that this point is where our origin is. This is where our x equals 0 is. And this is where this x is the point to which we have stretched the spring out to, right? So the stretch of the spring is just x. Let me just mark the stretch of the spring. It's fairly obvious. So x is just the stretch of the spring, right? There is a certain law called Hooke's law, which tells you how this force F that the spring exerts is related to the stretch of the spring. And that law is very simple. F is equal to negative kx. So in other words, the force exerted by the spring is proportional to the amount that the spring has been stretched out, right? So F is proportional to x. The k is the constant of proportionality. K is called the spring constant. and it's a measure of the stiffness of the spring. So suppose k is a very large number, then in order to stretch out the suppose k is 1000, right? So in order to stretch out the spring by 1 meter, then you would have to exert a force of 1000 times 1, which is 1000 newtons, right? That's a lot of force. But suppose k was only 1. In that case, in order to stretch out the spring by a distance of 1 meter, same distance, you would only have to apply 1 times 1, or 1 newton of force. So k it gives you an idea of how stiff the spring is. A large k means it's a stiff spring. It's very hard to stretch out, right? Okay, what is the minus sign? The minus sign simply tells you that the stretch of the spring and the force are in opposite directions. That's fairly obvious. Here you're stretching the spring, you're stretching the spring, so you're moving in the positive direction. That's stretching out the spring. The force will be in the negative x direction because the spring will want to come back. If you compress the spring, I'll draw that as well. Suppose I'd taken the same spring, but I compressed it. So in that case, my x would be negative, right? The force would be in the positive direction, and it would be given by exactly the same equation. This is called Hooke's law. Okay. Let's do one calculation involving Hooke's law, right? So, and this kind of puts together everything that we covered so far. So we are going to calculate the work done by or against the spring force, and this is the problem on slide 16. Okay, so what is the work? Okay, so I'll let you read the problem for a minute. I'll just pull it up here. So find the work done by the spring force when the spring is stretched from x equals xi to xf. The equilibrium position of the free end of the spring is at x equals 0. So let's think about that. So here's the spring. If you just leave it to itself, the end of the spring will settle at a point which we are just calling x equals 0, right? However, our spring is stretched out already to xi, right? So I'll just draw that. I could have drawn it here on the same diagram, but that would make it more cluttered. So I'll just draw. So this is what our spring looks like right now. So its end is currently at xi, and this is the x equals 0. Here is where it would be if you hadn't stretched it. Okay, and then what you're doing is you're stretching the spring from xi to xf. So this is how the spring looks initially. And then you stretch the spring out all the way to xf. This is how it looks like in the end. Okay, so what is the work done by the spring force? So the first question that I want you to think about and try to figure it out yourself before you listen to the answer is this work going to be positive or negative? Is the work done by the spring force going to be positive or negative? The answer is the work done by the spring force will be negative. You can figure that out without doing any calculations. How do we know that? What is the direction of the spring force? The direction of the spring force is going to be to the left, because the spring is always stretched out, right, as it's being, so it's pulling to the left all the time while you're in the process of stretching it out. So the spring force is acting to the left, whereas the stretch is happening to the right. So the spring force is not getting its way, which means that the work done by the spring force should come out to be negative, right? All right, so we already know the answer. We just need to figure out what the work is. So how do we find the work? Is the spring force exerting a constant force? The answer is no. Why? Because the spring force is given by F is equal to minus kx, so it depends on x, right? So as x increases, the force is increasing, so it's not a constant force, which means that we have to integrate. So the work done is going to be the integral of the force, the variable force over the displacement xi to xf, right? And so we had derived this earlier. So we can just plug this in. So f is equal to minus kx dx, and you're integrating this from x initial to x final. So that's going to be minus half kx square x initial to x final. These are the limits that need to be plugged in. And once you plug in the limits, you get minus half k x final square minus x initial square. And that's the answer. So that is the work done by the spring force. Now notice that this will be a negative number. This is guaranteed to be a negative number because x final is greater than x initial. So the quantity in the brackets is a positive quantity. K is a positive quantity, and you have an overall negative sign. So the answer is guaranteed to be negative, right? Which is exactly what we had expected without doing any calculations. So the work done will be a negative quantity. Okay, what is the work done by the external force that's stretching the spring? So the problem, so that's the second part of the question on the slide. And the question also tells us that the spring is being stretched with zero acceleration, right? So that means the person stretching the spring is always matching, let's call the force exerted by the person stretching the spring. That's the person who's holding on to the spring and pulling it. Their force always matches the force exerted by the spring, right? Because there is no acceleration, so that means the net force must be zero. Remember, F net equals mass times acceleration. So if there is no acceleration, the forces must cancel each other out. So F external for no acceleration. So this is the problem, the second part. No acceleration means that F external is equal to the force of the spring, right? So it's exactly the same force but pointed in the opposite direction. So that means if the force of the spring was negative kx, F external would just be positive kx, right? And so the calculation would be identical. And so the work done by the external agent would be exactly the same thing, but it would not have the minus sign. So it would be half k x final square minus x initial square. All right, so on slide 17, I have a very similar problem, and I would recommend that you try this problem out on your own. And that concludes our discussion of work. In the next video, I'm going to talk about kinetic energy. All right.